In this problem, we'll be working an application of an exponential function. It says when rabbits were first brought to Australia last century, they had no natural enemies, so their numbers increased rapidly. Assuming that there were 60,000 rabbits in 1865, and then by 1867, that number had increased to 2,400,000. So we have a couple pairs of information. We have a number of rabbits. We have a couple of years. The important part is that we are to assume the number of rabbits increased exponentially with the number of years that elapsed since 1865. So again, t of 0 is associated with the year 1865. That tells us that if we're having a time and a rabbit population, ordered pair, then what we should have is 0 and 60,000. And then an ordered pair of 2 and 2.4 million. The other key piece of information is that it says we should be working exponentially. So the general equation we should use is, again, the general equation is y is equal to a times b to the x power. So if we use our first ordered pair, we find that 60,000 is equal to a times b to the 0. We like to have b to the 0 because b to the 0 is 1, so that tells us that our a is 60,000. So to find the b value, we take the other ordered pair and get 2,400,000 is equal to our a value, which is 60,000, times b to the second power. So now we isolate for b. If we take 2,400,000 and divide by 60,000, we get a total of 40. So b squared equals 40. So b is equal to the square root of 40. Now usually we would say plus or minus the square root of 40, but again, because it's the base of an exponential function, we know that b has to be positive. So our particular equation, if we let t be time in years since 1865 and maybe use p for population, then we can say that p will be equal to our a, which was 60,000, times the square root of 40, all raised to the t. So the next part of our question says, how many rabbits would you predict in the year 1870? So again, our starting year was 1865. So to find t, we're going to take 1870 minus 1865 and see that t will be equal to 5. So we'll use that in our equation. So p will be 60,000 times the square root of 40 to the 5th. We could also rewrite that as 60,000 times 40 to the 5 halves, and that's probably what I'll do. When we do that, we find that the population would be equal to 607157310.8. Now we can't have 0.8 of a rabbit, so that means that we would have 607157310 rabbits. And on this one we are going to truncate the number rather than round it because we don't want to round up. That doesn't give us an extra rabbit. For part C, it says, according to the model, when was the first pair of rabbits introduced into Australia? So the pair is the key word because it tells us that p should be equal to 2. And this time we're going to be solving for t. Alright, so we'll start with that. So 2 would be equal to 60,000 times the square root of 40 to the t. So the first thing we do is divide by 60,000 and get 1 over 30,000. It's equal to the square root of 40 to the t. Now since we have a t and an exponent, we're going to have to take the log of both sides. So maybe we'll do ln because it's shorter to write. And then use the power rule. So we know that the ln of 1 over 30,000 is equal to t times the ln of the square root of 40. So t will be equal to the ln of 1 over 30,000 divided by the ln of the square root of 40. That gives us an approximate t value of negative 5.6. So that tells us that it happened in a year previous to 1865. So if we take 1865 minus 5.6, we're going to get 1859.4. Now that just means it's 0.4 of the way through the year 1859. So what year is it? It's still 1859. And that will conclude our review of our exponential equation.